Ladies and gentlemen, good morning. Welcome to the opening ceremony of the 3D printing seminar for building and construction and food and beverage industries, organized by the Hong Kong 3D Printing Association and implemented by Hong Kong Productivity Council, with the funding support from the SME Development Fund of the Trade and Industry Department of the HKSAR government. And the main objective of the event is to raise SME awareness and applications of 3D printing in their industries. And before we start, I would like to invite Ms. Amy Singh, Chair Lady of the Hong Kong 3D Printing Association, to give a welcoming speech. Ms. Singh, please.
Mrs. Katjes-Magic, distinguished guests, ladies and gentlemen, good morning. It is my great pleasure to welcome you all to the first seminar of our 3D printing industry-specific seminar series. Our focus today is on building and construction and food and beverage industries. I wish to extend a warm welcome and friendly greetings to all local and overseas speakers and participants. On behalf of the Hong Kong 3D Printing Association, I would like to take this opportunity to thank the Trade and Industry Department of Hong Kong SAR government, who generously supported our series of 3D printing industry-specific seminars and workshops. Through the SME Development Fund, the program will be key step to drive reindustrialization in Hong Kong and attract local SMEs to adopt technology. The Hong Kong 3D Printing Association, as the first registered 3D printing association in Hong Kong, takes the pioneer role to promote the image and capabilities of 3D printing technology in Hong Kong, serving both local academia and industries. 3D printing technology, also known as rapid prototyping technology, has been developed since the 90s and is gaining popularity over the last few years. With various cost reduction in the technology throughout the decades, 3D printing machines are become more affordable and penetrating to SMEs and household users. This technology stimulates creativity in product design, which also shortens product development cycle, reducing the cost of design verification and sample evaluation. With the ease of adapting to 3D printing technology, SMEs can enhance their competitiveness and generate a new business model as a result of these breakthroughs in the product design process. As a consequence, HK 3DPA has launched this project to support and enrich local SMEs' competitiveness in the international markets. 8 high-value industries with great potential in applying 3D printing in their operations are selected in our project, including building and construction, food and beverage, toy, game and premium gift, houseware, jewelry, eyewear, fashion and footwear. These seminars will provide comprehensive insights on the latest 3D printing technology and novel applications within various local and worldwide industries. The seminar speakers come from different parts of the world with strong industry backgrounds as well as cutting-edge research from university, which will certainly stimulate many new ideas. We hope you enjoy today's seminar and serve as a platform to gather specialists from different disciplines, which can bring new collaborating opportunity, enhance the all-over competitiveness of Hong Kong SME. I am confident that every one of you will find the upcoming seminars inspirational and rewarding. Thank you very much.
Thank you, Ms. Ling. Please continue. And may I now invite Mrs. Katjes-Magic, Executive Director of Hong Kong Productivity Council, the implementation agent of the project, to say a few words for us. Mrs. Mac, please.
Chair Lady Amy Sin, distinguished guests, ladies and gentlemen, good morning. On behalf of Hong Kong Productivity Council, a very warm welcome to the 3D printing industry specific seminar for building and construction and food and beverage. Excuse me. If I ask you to name some notable innovative facets of 3D printing, houses, chocolate, or bicycle may be some of your obvious choices. Well, passenger planes will soon join this list. Earlier this month, Boeing announced the commissioning of a Norwegian 3D printing firm to help this aviation giant print the first structural titanium parts of its 787 Dreamliner. The move is expected to help the aircraft manufacturer save up to $3 million in the production cost. More significantly, it is another example of the growing industrial confidence on 3D printing as a viable direct manufacturing method. Many advanced industrial nations are already proactively driving the development of this disruptive technology in recent years, integrating it with Internet of Things and smart manufacturing to bring revolutionary changes to industry, business, and consumers. Hence, in order to stay one step ahead of their competitors, Hong Kong businesses must quickly equip themselves with the know-how of 3D printing and be adventurous in utilizing the limitless application it offers. At HAPC, we have been on the forefront in supporting the local industry to adopt 3D printing in their operation. On top of raising the awareness of the proliferating innovative applications of the technology, we have wasted no time in sharpening our competence by investing in our hardware facilities and R&D efforts. For example, we set up the first one-stop 3D printing support center in Hong Kong. The 3D printing one at the LG1, the lower ground one, level of this building in August 2015. Home to the widest spectrum of software and hardware, with capacity for multi-colored, multi-material 3D printing, being backed up by a wealth of HAPC's expertise in technology application. The center offers users the opportunity to bring their creative ideas to life. Do spend some time to pay a visit to 3D Printing One after this seminar. At the same time, our 3D printing service capabilities are being continuous upgraded to meet the ever-changing market needs. Very soon, Hong Kong's first high-end titanium 3D printing system for open use by industries will be installed here at HAPC. Local manufacturers eyeing on business opportunities in precise medical implants, super light critical components, customized sport equipment, tooling, and other high value adding products will benefit from this new setup. Meanwhile, our R&D experts are bending their heads on the research to make metal 3D printing more affordable. I expect the result of the development of a cost-efficient 3D printing metal powder will be out soon, so please stay tuned. Today's seminar will provide a valuable opportunity for the local construction and catering industries to keep abreast of the latest development of 3D printing. I wish all of you will be better placed after this seminar to seize on new business opportunity arising from this disruptive technology. Finally, I would like to thank the Hong Kong SAR government, our honored speakers, the Hong Kong 3D Printing Association, and all supporting organizations for making this event possible. I wish you all a very inspiring and rewarding experience. For our international speaker, I would like to invite you to enjoy all the good food in Hong Kong and also try your best to contribute to our economy. Go shopping. Thank you.
Please remain on stage and 大家好。 remain on stage to present the souvenirs with Ms. Amy Singh to our speakers. Ms. Singh, please. First of all, we would like to invite Professor Christopher Tuck, Professor of Material Engineering, Faculty of Engineering, the University of Nottingham. Yes, Professor Tuck, please remain on stage and wait for the group photo later. And Mr. Ronald Rael, CEO of Emerging Object. Thank you. Ms. Melissa Snover, the Managing Director of Katjes-Magic Candy Factory. Thank you, Ms. Snover. Thank you, Ms. Snover. Please remain on stage. And Mr. Patrick Ng, Director of Power Lab, LWK and Partners. Mr. Ng, please. And Mr. Michael Wong, Manager of Strategic Marketing and Business Development, Welfare Electronic Component Limited. And Mr. Chuck Fong, he is also our technical host today, and Senior Consultant of the Smart Manufacturing and Material Technology Division of HKPC. Thank you, and may I now invite other speakers to take a group photo with Ms. Singh and Mrs. Mac. One step forward, yep. Thank you. Please remain on stage. Don't come down first because we would like to invite our representative from supporting organization to take a group photo with all of you. May I now invite a representative of the following supporting organization to come up on stage. The Hong Kong Construction Association, their representative. The Hong Kong Construction Material Association. And the Hong Kong Federation of Innovative Technology and Manufacturing Industries, Mr. Lian Fat, and then from the Hong Kong Federation of Restaurants and Related Trades, the Industrial Designers Society of Hong Kong, the Hong Kong Food Council, and the Professional Validation Council of Hong Kong Industries, please. Yeah, we may now take this group photo. Thank you. Thank you. Thank you very much. And you may now leave the stage and please seat it. And many thanks to our officiating guests, speakers, and supporting organizations. Thank you all for joining us today. The 3D seminar in building and construction, food and beverage industry will begin shortly. And may I now invite our technical host, Mr. Chuck Fong, Senior Consultant of Smart Manufacturing and Material Technology Division of HKPC, to host the seminar for us. Chuck.
Thank you, Betty. Thank you, everyone. And thanks for all of our officiating guests, speakers, and supporting organization. I'm not going to introduce myself again, but before the seminar starts, I would like to announce a switch this morning. The presentation from Melissa and Ronald will be switched. So we will have Melissa first, and then we will have Ronald after the first break. So our first speaker will be Professor Christopher Tuck. I would like to introduce him first. Christopher is the Professor of Material Engineering in the University of Nottingham in the United Kingdom. He is also the Deputy Director of the EPSRC Center of Innovative Manufacturing in Additive Manufacturing, and currently running numbers of projects based on around the manufacturing of multi-material and multifunctional inkjet printing, and also nanoscale additive manufacturing system. He will provide us an in-depth knowledge on the latest development of 3D printing technology, as well as the corresponding application and methodology in building and food industry. Professor Tuck, please.
Thank you. Thank you very much, John. My name is Chris. I'm coming to you from Nottingham in the UK. And so what I'm going to do is give you a bit of an introduction to our Centre of Additive Manufacturing. We call 3D printing additive manufacturing in the UK for a number of reasons which I won't go into now. But what I'll do is give you an overview of what we're doing in Nottingham. A lot of it which is not really directly applied to building and food, but has a tangential impact for what is possible with additive manufacturing and could be used in those kinds of industries. So that I'll take you through where we are in terms of single material additive manufacturing, single material 3D printing, and then move towards what we're mostly interested in at Nottingham, which is multifunctional printing, or some people call it 4D printing, but actually we're interested in multi-material type examples. And then I'll finish off with some summary and conclusions. So, in terms of who we are a group, a research group that is around about 100 people, around about 65 PhDs, about 25 postdoctoral researchers, 7 faculty, and some admin and technical staff. And we were established as a rapid prototyping group in the 1992 at the University of Nottingham, and then went round at various number of universities in the UK, and ended up back in Nottingham in 2012. And currently we host two centres of additive manufacturing, which helps underpin our funding. EPSRC is the Engineering Physical Science Research Council in the UK. It's our main science funder for work in universities. And so we host the EPSRC platform grant in additive manufacturing, and I'm also the director of our doctoral training centre in additive manufacturing, where we're training around 70 PhD students in additive manufacturing over a 9-year period, so a large number of students coming through the group. And we have around about £20 million worth of funding today. About 15 to 20% of that is direct from industry, so we do a lot of direct industry funded research and development. We try to think about research as being having a research focus, but it's industrially driven by applications, by understanding what people require from additive manufacturing, and where the science then leads us into good science work. We also formed a spin-out company in 2015 called Added Scientific, which is a technical service and consultancy company to allow people to understand and to educate themselves and to get the best out of these types of technologies. You can see a few pictures on the right-hand side there of the lab, some of the single material, but also the multi-material systems that we have available. So, where we are. So currently, we have a range of technologies that are very useful for fast prototyping, for fast realization of very complex goods and services. We are really at the point where we can pretty much build the geometries that anybody really wants us to be able to do. But there are a lot of secondary factors that are starting to come into play that are really starting to dominate what's happening. So the good example of Boeing using titanium, we heard from Magnus earlier, is a great example, because we've been able to make those structures and make those parts for a long time, for probably about 10 years. But what we haven't been able to do is understand how they differ from those that would be traditionally made. And so a lot of the work that we're seeing at the moment is trying to understand how the processes differ and how the processes affect the components that are coming off those machines. And so we're seeing a lot of advances in simulation, characterization, microstructural analysis for metals, and composite material processing as well. And we're just starting to uncover a lot of issues that are now starting to be understood. Why microstructure develops, why strength is different, why elongation, break is different. And this is just as relevant to the building and food industry, because what goes through the machine is important, but what comes out of the machine is the most important thing. So understanding that material process interaction is critical for the success of any product or any type of application where additive manufacturing or 3D printing is going to be used. So this is just a couple of examples that show you, oh, not that one. Oh, there we go. Show you what kind of structures are interesting from a metals point of view. So the spinning round box here that you can see is an X-ray CT image of something that's come off a metal machine. So this is made in aluminium. And at the bottom left, you can see that CT taking slices through that component, and you'll start to see small black dots appear as you're going through the component. And those small black dots and the little areas of grey that you can see in the middle are porosity. And so porosity is void in our machines, in our components, and it's really the real problem with using additive manufacturing, because you don't know that you've produced it until you do analysis like this, which is very expensive and time consuming. And so what we're able to do now is start to use these tools to understand our processes better, understand what is made, and then reuse that information to make the process better in the final product. So even with the level of porosity you can see in these are 99.995% dense. So they're very dense in comparison to most casting materials that come off conventional processes. But even because of that, because this is a new process with new materials, we're still a little bit nervous about using things that aren't 100% dense, not that we ever get to 100%. One of the reasons for that porosity is that we have different activities going on in the process. And so one of the things that we have when we're processing metals is we have a really nice, very pretty little firework going off as the laser traverses across the bed. So we have this little explosion happening every time we hit the bed with the laser light. But what that means is we create something called laser spatter. And these large lumps here, are about 3 or 4 times larger than the standard powder that we use in the process. And because of that, these particles get trapped and they don't melt as easily, and then they cause porosity. So it's another example of how that can be problematic. We're also able to take, from a polymer point of view, from a plastics point of view, starting to be able to put in composite fillers and other fillers into the material, so that we're able to then produce much higher performance materials like these, which have been produced by my colleague Ruth Goodridge, which are carbon nanotube filled and carbon nanofibers and whiskers filled into standard polyamide powder, so nylon powder. So whereas you could do this with conventional moulding, you can do this in a laser sintering and still get the complexity of components that you might want to design in your final product, and give you much better mechanical or thermal or different properties in those components. A key advantage of using 3D printing, and one that I'm going to try and expand on later, is the fact that you don't have to have the same material all the way through a component. So this is some work done by one of my colleagues at Nottingham, Adam Clare, where we're taking sections in a component, this cylinder here, and we're actually being able to change from material A to material B to material C to material D to material E. And again, this is something we've been able to do for probably 10 years or so. But what we're not so sure about is what happens between A and B, what happens between B and C. So the material aspects that change the structure going through that component. You might want to do this, for example, for having different wear characteristics or different thermal characteristics or different structural characteristics going through your component. It's something we can do, but something we don't necessarily understand very well. And so as I mentioned before, we're starting to develop a lot of methods to look at how components that come off the machines differ to the original design intent, so the original CAD. 3D printing, additive manufacturing is driven by digital data. We need digital data to drive the machines, and if we don't have it, we can't produce anything. The fact is, though, that digital data is realised in a physical way in the machines. And so what you get out of the machines will be slightly different because of shrinkages, because of thermal stress, because of all sorts of different problems that go on in the machine. It will have a different structure when it comes out of the machine, and understanding that enables us again to go back into the machine, to change what happens in the machine, and to try and make the machine more reliable, more repeatable, and moving further forward, hopefully lower cost because we'll have less waste in the machine. Another benefit to using additive manufacturing is the fact that we can do something called in-process monitoring. So whereas with almost every other traditional manufacturing technique, you put in your raw material and you get out your final component, you control what goes on in the process. Here we can actually, in additive manufacturing, we can see what goes on in the process. Because we build layer by layer, we can take images or we can take optical measurements during the process and really start to understand where things have gone wrong or where things are not quite as they should be in the process. And this is something called spatially resolved acoustic spectroscopy. I'll be asking questions on that one later to make sure that you're paying attention. But this one allows you to look at how the microstructure changes, how it develops in a metal process to make sure you're getting the right kind of components out. Again, this might just be some optical images that we're taking, some photographs that we're taking to make sure it looks the right shape and the right density. But this is just a more advanced version of that. So all of this work really leads up to why do we bother with additive manufacturing? Why are we interested in it at all? And we are interested in it at Nottingham because we want to be able to build things like this that are phenomenally complicated, but not complicated for no reason. They're complicated because they're higher performance. So again, Boeing are doing this because they want lighter weight components on their vehicles or aircraft, and so they use design algorithms such as topology optimization, which is how these have been developed, to really reduce the weight on those components. And additive manufacturing is the only real way of being able to realise the complexity in the component and realise that physically. Again, you can start to introduce structures that would be impossible to make in a standard manufacturing technique. So these can be used for filtration. I'll talk about these a little bit more later on. Oh, there's more design optimization in the bottom. So where are we with building and food? So there's been quite a lot of activity in building and food, excuse me. And these are just some examples. You'll hear a lot better examples, I'm sure, later on. But these are some examples that you can see. This is a metallic structure that is being developed in Holland. It's going to be developed as a bridge over in a park, I believe, and it's a metallic bridge, and this is just a scaled version of that. All of these processes have the same issues that I was talking about before with the metallic and with the polymer processes that we have for standard additive manufacturing. You need to control the raw material, you need to control the environment that the process is happening in, and you need to ensure the accuracy and repeatability. I don't think any of these really are contentious. For building specifically, atmosphere and the environment are key elements to this. So particularly if you're building metallic structures, where if you have oxygen in the environment, or you have high levels of moisture in the environment, that can drastically affect the material properties of the components that are coming off your machine. So it's a great idea to be able to build a bridge out of a metal printer, building it as it's going across the over the river or gap, whatever it might be. But controlling that is going to be really, really hard, and there's a lot of challenges in being able to do that. Similarly, controlling the material as it's going through the machine, as you can see with this extrusion-based system here that's building houses, controlling the material so that you have the right kind of levels of mechanical properties, compressive strength, and all that kind of issues is key. And it doesn't change with food. In fact, in some ways it gets even worse because we're eating it, so we want to make sure it's not going to do anything badly. Okay, so so just to set the scene, these are some examples that that I've been able to look at, and most of these examples are based on 3 manufacturing types. So these are the should be 7 additive manufacturing categories that are defined by the standards group ASTM F42. So these 7 categories are the different types of processes that we have available for additive manufacturing, and most of the food ones, and actually most of the building ones, are actually manufactured using these types of process. So material extrusion, which is what we commonly know as the consumer 3D printing, powder bed fusion, and the metallic kind of systems, but also sheet lamination, where we're putting a sheet across the bed and then cutting out its shapes and then merging them together, and then actually another one which is binder jetting. We actually do have some work going on binder jetting for food in Nottingham as well, but I'm not going to talk about that today. So in terms of processes and food specifically, material extrusion is probably the one that dominates the application so far, where we're using a filament of material or a pellet or a paste or a formable liquid to directly squeeze out, like a cake icing type method, to produce our layers in the component, and to then solidify that component together to give us our final shape. One of the things that's really interesting for me in terms of food is normally a foodstuff isn't made from one thing. It's not just chocolate. There'll be some nuts in there, or some caramel, or something tastier, I don't know. Or it might be something that's made from different levels, different types of sugars, or different types of fats, and different types of proteins. And so here you can see some further examples by Cornell. Again, by using paste-based methods, some gummy sweets, which we'll hear about again later on, but also pasta. Pasta that's been done by a company called Barilla and the research organisation TNO in Holland. So all of these elements require significant control, significant amounts of significant challenges in being able to put the right material in the right place at the right time to give you the right performance, regardless of whether it's building food, whether it's rocket engines for spacecraft. It's all about controlling where and when the materials are put down. This is another example. So this is binder jetting. So here what we're doing is we're printing into a powdered material, in this case sugar. So we're printing into sugar different colours, but also with a binder that's edible. So you can produce lots of different shapes and sizes and different designs and all sorts of different things. And then finally some sintered versions. These ones, which I think always look like coral to me, but this is actually sugar that's heated up and with a hot air gun by the evil mad scientist laboratories in the US, and then some other versions of that where we're trying to sinter and melt particles together using thermal processes. But again, these tend to be single materials, single elements of materials going in there. So we're kind of limited in the types of products that you'll be able to produce. Very beautiful designs, very innovative designs, lots of consumer-driven capability here, so you can have consumers come in and develop those, but actually a single material product without any further assembly happening. So the issues associated with these types of techniques are very similar to those that we saw for building food. It's all about controlling the initial feedstock, controlling the regulations, so understanding what regulators require from the component, from the materials and the processes. Size is a problem. So we tend to eat things that are centimetres in size. That's fine. But actually, the individual components that go in them can be anywhere from less than a micron. So a fat molecule or globule is less than a micron to give the right mouthfeel when you're eating it. And so actually what you want to be able to do is control dispersion and size from almost the nanoscale all the way up to the centimetre scale. And that's really a very, very big challenge in a process like additive manufacturing, unless you can use conventional feedstocks that have that inbuilt into them. So, no products are limited to single materials. So what about multi-material, multifunctional additive manufacturing? So what I'm going to go through now is a lot of research that we're doing at Nottingham. A lot of it is not based on food, it's not based on buildings, but hopefully you'll be able to see that there's a direct relationship between these aspects and what the seminar is about today. Before I start. So, conventional printing isn't single material either. So conventional printing, like desk-jet printing, is multiple material. We see that in terms of different colours and different pigments that are printed onto a 2D piece of paper. We can take that type of process and move that into 3 dimensions. So what we use is inkjet printing techniques to be able to print discrete droplets of a material in one place, surrounded by other materials of a different type. And so we use inkjet nozzles, inkjet printing systems that are normally piezo inkjet systems, like the ones you might get from Fuji or from Konica Minolta, any of those kinds of standard heads, to be able to print down those materials and place them where we want them to be. And in terms of resolution, here we're able to print things that are sub 50 microns in size, as in the X and Y directions, and less than 10 microns in size in the vertical direction. So we're getting close to the kinds of resolutions that I was talking about a moment ago. We're also able to print quite large structures if we wanted to. So I'm guessing the multicolour printer you have downstairs is an inkjet-based machine. Yeah. So very similar to that, but rather than colour, what I want to do is be able to print any material, which is a different kind of challenge. So we have a lot of different projects ongoing with this, from printing structural materials that are infrared or UV cured, pharma materials with biological aspects, but also electronics as well. So the interesting thing to understand about inkjet printing is most things can't be printed. They're too thick, their viscosity is too high. And so what we have to do is lots of work in the material space to reduce that viscosity down to a point where the material can flow through a head and be ejected from the nozzle. So here you can see some examples here of wax that's been printed. There's wax that goes into the head, is melted up to its melt point, and the viscosity drops down, and we're able to print out droplets of this. And what we're looking at is lots of materials and chemistry challenges. Before we get to that stage, we need to be able to design for these structures. So at Nottingham, we've also been developing the design side as well as the process and materials side. And these structures that you can see below, with these very complicated structures that are formed, we can quite easily produce using some design software that we are developing as part of an Innovate UK funded project. So this is called Flatpak, and if anybody wants this, please just email me and I can get you a free copy to evaluate. It's only got a limited lifetime, but you can certainly have access to it. Where we can choose from a range of different cell types. So from this double gyroid all the way down to, no idea what this is, lidinoid or whatever it is. But these are all something called triply periodic minimal surface structures. So again, that's the one for the test later. These structures are surfaces that interweave, and they're very interesting because they can separate space, they can have very low volume, but also you can run different fluids through different elements of it, all sorts of different things. And our software basically enables you to choose one of these, or two of these, or three of these, and populate your design space with them pretty easily. And so here you can see changing density to change the modulus, to change the mechanical properties, but also we can grade that density through a component from fully solid to a given density measure. Or we can do that in a varied kind of way, so we can do this in a sinusoidal way as well. A different way of going about this design is to understand what the different design competing design constraints are that you have in your product. So for this example, this is a structural analysis that's lightweighting a component, but it has also a electrical conduit which has a minimum distance profile embedded in it. And so what it's trying to do is compete with the lowest lightweight structure for the structural, but also the shortest distance for this electrical conduit that's in there as well. And so we have this system again at Nottingham where we're able to do multiple objective optimization to really start to expand the design space for any kind of application. It may be that you don't want electronics to be optimized, but you maybe want to do thermal analysis to be optimized, or it might be placement of different materials to give a different flavor profile through an optimized component, or an optimized product rather. And you end up with things that look like this. So this is something that our students designed about 4 years ago, where you can see that the dark elements are the electronics and the see-through are the structural. And this is the kind of thing that we'd like to be able to produce, but we just can't. This is printed on in basically black and clear plastic at the moment. So if these were electronics, then we'd be really happy, but they're not. So that's what I'm moving into now. So we're able to produce, with this inkjet printing type method, we're able to produce a wide range of different materials. We're able to print a wide range of different materials, and so what we can start to do is tailor how these materials are delivered to the component. Here you can see this waffle structure, we call it a waffle structure, which has a structural material, and then the black areas are silver. And you might ask why you want to do this. Well, this is actually a very useful method of tailoring the electromagnetic properties of a component. So this is using this kind of technique to change the relative permittivity of the component, which is really interesting in terms of metamaterials, for antenna, for electronic screening and shielding. You can do all sorts of different applications with this kind of technology. You can also start to build sensors into your components. So this is a electroactive polymer printed into another polymer, and then silver printed into another polymer that's flexible. So you can start to building flexible sensors that might be required for structural monitoring of your components, or structural monitoring of your buildings, or something like that. That you can then print into structures as you're going through, or add them on later, because they're the right shape, the right conformity to the particular pattern that you're interested in. And this example just really shows you how we move from 2 dimensions. Printing electronics in 2 dimensions is actually quite simple, relatively. The materials are not necessarily the greatest performance, but it's quite simple to do. And so you're able to print these 2-dimensional structures and then add in components like batteries and switches and LEDs. But what we really want to be able to do is print in this 3rd dimension. And that's much more difficult. But something we've been able to do at Nottingham is be able to do this and then add in structures later on. So here you can see a capacitive touch sensor that's got an electronic conduit that goes down onto the Arduino at the bottom. I should play that again. And so you can see the capacitive touch sensor completes the circuit, and then you've got some electrons running through the circuit, and the lights light up. So that is a potential possibility for adding in further functionality into a component. But printing in this vertical direction is much more difficult. So we've spent about 3 years being able to build up with metals in a printing type system. And here you can see about 5,000 layers of silver in the vertical direction, which is able to take a current. And actually we have now different ways of printing these so that it takes less time. This would have taken overnight to be able to print that high, which is only about 3 millimeters, so it takes a long time. But we're now able to do this a lot faster than we were before. And we're also able to change how the microstructure of the material really develops by doing in-process methods that enable us to get to this nice continuous structure. Obviously this is really bad for electronics because the electrons won't go in that vertical direction, they get stuck at the boundaries. Taking that further forward, what we can do is start to build transistors. So we've seen quite simple circuits, but now we're moving towards being able to print transistors that have then the effect of being able to print switches within a circuit. And so we're moving towards being able to print these transistors into a component, and so then you can effectively have logic gates and hopefully one day a printed sort of microchip design. And you can be able to spatially move those components throughout the system to be able to understand where you need them, where you don't need them, and get the right, more optimum design. Finally, in this kind of electronics area, so what we're able to do is print the circuits, we can print the some of the components, so we can print batteries, we can print resistors really easily, we can print transistors relatively easily, but what we're also able to do now is print light. So these are fully printed structures that are on a flexible substrate, but which could be incorporated into a 3D printed element that have got basically a phosphorus ink that's been inkjet printed, and so we can start to print lights throughout a component. So we can print the individual circuits, we can print the transistors, hopefully print the batteries, print resistors, and now we can print the illuminating components. So that's taken 5-6 years to get to that point in terms of research. But obviously, working in the university, we try and do as many different things as we can. And so this is just an interesting sideline to the electroactive printing that we're interested in being able to do. So what we really like to do, instead of those inks that you saw that took overnight to print a few millimeters in height, they're made from a nanoparticle suspension in a material. What we really like to be able to do is actually just print the metal. And we can do that with powered bed systems. If you want to be able to print multiple materials, they don't work, because you can't spatially print in different materials very easily. So we have a process at Nottingham called MetalJet. And basically this is the same kind of process that is printing an inkjet printing type process, but we're actually printing metal direct from melt. And so we have a collaboration with Canon OSE where we're printing three-dimensional structures using a print head that runs at around about 1800 degrees C to deposit metals directly. And here you can see one day, maybe, try it again in a second. You can see in this video, if it works, oh, there we go. Yeah. So you can see this is a metal droplet that's been dropped from just above here at 1500 degrees C and landing onto a copper substrate. So this is a tin droplet that's been dropped down. And we have an accuracy of around about 5 microns. So we're able to really move the production of metal substructures further on. And here you can see some of the droplets. You can actually see the recoil kind of vibrations that's gone through the droplet as it's landed, and then the kind of scalloping effect that you see there as well. Another area which is actually quite very close to the food area is because we're wanting to print different materials next to each other. Well, why don't we look at printing, rather than electroactive materials, biological structures and pharmaceutical structures? So one of the reasons why we do this is for drug delivery. And we have some projects that are ongoing that are looking at printing basically tablets. But not tablets of ibuprofen or tablets of paracetamol that you would normally buy in the chemist or the pharmacist. Actually being able to print very high value drugs that are that have customized elements to them for the individual patient. So rather than giving everybody the same dose via the same pill, you're able to change the dose for each individual patient, but only really for very high value drugs like cancer drugs, HIV and things like that. It limits the cost of those tablets, but also increases how effective they are for the individual patients. So just going even further down the resolution scale, this is some. I'll sort this up. There we go. So this is some work we're doing with nanoscale additive manufacturing. So really pushing the envelope in terms of the smallest thing we can manufacture. And again, when we're talking about food and being able to print single micron elements of fats that give us the right mouthfeel, or salts or sugars to distribute different tastes, then this is a potentially interesting method to do that. So this is something called 2-photon lithography, and I won't explain the physics behind it now. I can do later if you want, but I really wouldn't. Basically, it's similar to the UV type processes like stereolithography, which you might have seen, which you probably have in your labs here. It uses, but instead of using UV, it uses infrared light to develop the structures. And here are some structures you can see that are printed on that system. So if you look at the scale bar, these are around about a micron in size. So these grids and structures that we can print are really interesting, particularly if you can start to fill in these gaps with something else. So you can start to add in different materials by adding in different coatings to be able to produce really different types of products and structures. The problem with this process is that you can't build very big things. You can be kind of that big, so a few millimeters inside. But it is relatively scalable. There is a scalability potential with it. And also, we don't have to just build one component, one material component. We can do multiple material components. So we can start to print in metallic components into these nanoscale structures that really give us different metamaterial type properties. And these are polymer structures that have gold embedded in them. So these can act as sensors and act as different biological structures that we can use for scaffolds and all sorts of different things. So lastly, in terms of the 2-photon, this is again pretty much bespoke to Nottingham, is we have this 2-photon lithography method, but we also have something called a set of optical tweezers. So optical tweezers are like they're like Star Trek tractor beams, but only on a very small scale. So they don't pull in spaceships; they pull in little balls of whatever material it is. So this optical trap picks up this individual particle and can move it in 3 dimensions with light. So that's how it works. And what we've done is been able to couple that with our 2-photon lithography system to glue it in place. So we can start to glue in different particles of different materials into one place and start to be able to make these really complex structures with these additional elements in them. This may work, this may not. Give it a try. Yeah, there we go. So the green dots are actually the dots that we've pulled in with our optical tweezers, and then there we go. Excuse me. And then we've set them in place with the 2-photon. So what we're really starting to do is build from almost a nanometer scale, build materials up so that they have particular types of properties, or particular types of process characteristics. So just to start to summarise, how do all of these previous methods really affect building and food applications? Well, all buildings are inherently multifunctional. This is an example of homeostasis for intelligent buildings. And what hopefully you've been able to see is all of these different methods, whether they be single material or multi-material, can start to be incorporated at different length scales. But what we don't really understand is, and maybe understand later after today, is how that these can be really implemented, how that they can be implemented into the system, particularly with buildings, because you have such huge scales in comparison to additive manufacturing processes today. What are the real practicalities, what are the real practical challenges of being able to do this in terms of getting those multifunctional, multi-material structures in there? And the same with food. We have multiple ingredients, we have multiple components that have to be incorporated in the right way, with the right process conditions to make the material as functional, i.e. have the right taste or right structure or the right feel, as possible. How do we have the potential to be able to distribute taste, we have the potential to distribute things like folic acid for fortification, or even something called nutraceuticals, where we're actually able to print in clinical benefits into food for people who are maybe the elderly or to pediatric medicine, to make it more palatable to take that type of medicine. So really, in terms of summary and conclusions, there's a lot of different opportunities for materials development, for materials qualification. There's a lot of understanding now being developed to be able to start the material process design and to manipulate material response for a given application. We are now starting to see lots of material specific research becoming more common, and new methods of depositing materials is really quite key to developing that multifunctional side of things. The multifunctional, multi-material distribution type processes are much more challenging than the single material, because we have to look at how the materials sit together, how they react, how they merge, and really what are the different methods of depositing, different methods of post-processing and consolidating those materials. Really, really important. And really the opportunity is to understand what happens at the interface of the different applications, but also what happens at the interface of the different materials that are being printed together. Just for information, this is a conference that we have in Nottingham in July. If anybody's in the UK at that time, feel free to come and see us. And a few acknowledgements from some members of our group, not everybody. There's a lot of names there. And I'm free to take some questions if that's okay. Okay.
Thank you very much. So, any question from the stage? Or you can ask, okay, someone. Someone have questions?
Hi, Chris.
Hi.
About clogging, clogging, you get troubles, having jam, nozzle, clogging nozzle, things like that.
Yes, particularly with the inkjet processes, it's a big problem. So we run to certain material development rules that we have. So for inkjet nozzles, we have a maximum particle size of about 4% of the nozzle diameter. So our silver particles, for example, are around about 40 nanometers in size, so they're very, very small. And the loading percentage, so we also have a viscosity limit. So our viscosity is normally 20 centipoise. So if we're in that region, then generally we're okay. But depending on the solvent that we're using to carry the materials through, or the carrier fluids, if they're fast evaporating, that can be a problem as well. So it's a balance of getting evaporation of the carrier fluids, the size of the particles, as well as the viscosity of the overall fluid.
And then how do you clean the nozzle? Because you're using different materials.
Yeah.
It's very difficult.
Yeah. So we don't clean the nozzles.
Throw them away.
Yeah. So what we would have is for each different material, we would have a different inkjet head.
Okay.
So we keep the same material in the same head, so that we don't have any cross-contamination.
Oh, I see.
So with inkjet, if you're in production, that's okay, because you can have, they're very reliable print heads, they're very reliable structures. As long as your ink is designed correctly, then you should be fine. From a research point of view, it's very expensive because those inkjet heads can be thousands of pounds. So what we tend to use is something called a Fuji Dymatics head, the DMP 2800 heads. They are only about $100 US each, so they're a little bit easier to deal with.
My last question. You mentioned you were using special material. I can't remember now. 1800 degree.
Yeah.
So in that environment, everything will be melted around the printer head.
Yeah.
So you can't use plastic or use proper wire.
Yeah. So we're looking into being able to print onto ceramic filled plastics and ceramic materials as a dielectric layer. But we're also looking at using polyimide as a print base as well. So another issue is, as well as temperature, is also adhesion to the surface, whether we get adhesion at those temperatures as well, and how much degradation happens.
Hello, Chris. I want to ask the similar question. May I know the lifespan for nozzle jet?
Sorry?
Lifespan for a
The
nozzle
lifespan.
jet.
On our large frame printer, we have the same knob. I think we're running at 2 years at the moment. But again, we keep the same material. You can flush the heads. You can repair them a little as well. So, but they don't tend to go down very quickly unless we're doing something very aggressive in the head.
Okay. Any more questions? Okay. Thank you, Chris. So, may I introduce our next speaker, Ms. Melissa Snover, to deliver her presentation. Melissa is the managing director of the Katjes-Magic Candy Factory. The Magic Candy Factory brands create the world's first 3D printer for gummy candy and launched into the market, which amazed the world in 2016. She will now share how 3D printing could be applied in food and beverage industry successfully. Melissa?
Thank you so much, Chuck. Hello, everybody. Thank you so much for having me. That was a very interesting talk by Christopher. I'm going to focus a little bit more about the way that we take 3D printing technology and we aim to make it mainstream approachable by making it easy for anyone to use. Because as you will have noticed from the previous presentation, high-level 3D printing is very technical, and actually the mainstream market will not bear the burden of learning those things. So if we want this to be used by lots of people, if we want it to take off like the smartphone did, we need to find a way of making it easy for everyone to use, and that's where our vision comes from. So who am I exactly? I'm actually a serial entrepreneur who started her first company when she was 23. I developed the world's first vegan gummy candy range called Goody Good Stuff, and I sold that about 2.5 years ago and joined forces with Katjes, who is a beautiful family-owned company based in Germany that's been making candy. And we came together in order to create a way for people to be able to create their own candy. One of the biggest things that is frustrating when you're a mainstream manufacturer is you cannot really make anything unless you're willing to make about 1 million bags of the same thing. Otherwise, it becomes such a huge price point, the consumer can't bear it. So we looked at lots of different technologies, and 3D printing won the day. But really, up until 2 years ago, I knew nothing about 3D printing. I read every single book available on Amazon on 3D printing. I bought several 3D printers, took them apart, put them back together, went to every maker lab, joined all the chat forums, talked to fab labs, pioneers across all different levels of the industry, and actually built my own prototype and relearned coding processes and G-coding and slicing, and was able to develop this system probably from a different way that a lot of people approach 3D printing. I started with the consumer and went backwards and found a way for 3D printing to be able to solve their needs. We actually developed the first prototype in under 6 months and launched the first, and still to this day, the only 3D food printer which is available for consumers to use in commercial environments. Katjes, just a little bit about Katjes. Katjes is a business that was started 100 years ago. It's still run by the same man whose great-grandfather started it. It's a 100% family-owned business, and they are pioneers in innovation, naturalness, and vegetarianism. And RJV, the way that it works is we run as a totally standalone company, but we have the support of this amazing business behind us, which is really a wonderful business model, and I encourage bigger companies to look at it also in the future. So you guys probably know all this stuff. I talk to huge different varieties of people when I talk about what we're doing, and so I like to give a tiny bit of background, but you probably already know this, so I apologize for teaching you to suck eggs. But basically, 3D printing was invented long time ago. It was under a patent protection used mostly for prototyping in industry, and around 2012 it started to take off again, and there was this massive amount of excitement. 3D printing is going to change the world. Everybody's so excited. Now, where we are at the moment is what they call the trough of disillusionment, which is where the mainstream market has been excited by the idea of 3D printing, but tried to use it, and it's super hard to use in general. You need a bunch of knowledge about CAD designs, material behavior, slicing, coding, etc. And also, in general, regular 3D printers are still extremely slow. So the mainstream market has now become a little bit disillusioned. The market size is huge and it is still growing, but the majority of this growth is not the consumer market, it is industry. And our goal is to be able to use 3D printing technology and principles in order to actually solve consumer problems and make it fun and easy for them to become their own creators. The examples that Christopher showed of other people doing 3D printing of food are, of course, we know all of them, but they are not really available for the customer to go and use these in places where they can create something of their own. Those are being used for things like prototyping, they use them for expos to create PR excitement. The Hershey's printer, which makes chocolate, which I have seen up close, they developed it with 3D systems. It takes them 45 minutes to make something about this big, about the size of a Hershey's Kiss. So as far as applications for the real consumer retail market, it's super cool, they look awesome, but it's not actually, useful in a real life situation. And that's what we aim to change. The age of usability is the key to the next stage of where we go with 3D printing, and that is really, we aim to use gummy candy as a medium in order to do that. We all know their smartphones were around for about 7 years before they took off the way that they did. What changed that? iOS systems, operating systems, Android, which made the technology easy to use, enjoyable to use, intuitive for the consumer. And that is the challenge right now with 3D printing, is unless you have a degree in it, or CAD design, or a massive level of enthusiasm, which there are those people, but they're not the mainstream market. So whoever takes this problem on across all different kinds of 3D printing, food, FDM, PLA printing, home use, creating tools at home, whoever makes it easy for the design and printing process to be perfect every time, and whoever can speed it up to increase usability, they will own that part of the sector and industry for the future, in my opinion. So how was Magic born? That's Mr. Facine, that's me, and that's Mr. Adine. These are my development team. Mr. Adine helped us develop our ingredients. I came up with the software and the hardware, and Mr. Facine has a huge amount of industry expertise in confectionery, and he was helpful with that. So basically, what did I do? I developed the first prototype printer. I actually used a shell of a glue deposition machine, if you can believe this, that was being used to apply glue for cars, like double mixture, high intensity epoxy glue. And so I used basically a shell of that, implemented a special extruder base, and launched this into the market in Berlin in the summer of 2015 in order to basically test, what is the consumer reaction? Are people ready for 3D printed food? Are they going to kind of be freaked out by it? Is it too scientific? How can we make it so that it's really enjoyable and really well accepted by them? So I moved to Berlin, and I actually worked as a retail associate or a shop worker in this store for 3 months, and I watched the faces of every consumer. I watched the way that they reacted to every single different thing that we tried during that 3-month period, and I learned a ton. The first prototype that I developed was I say slow, it was still faster than Hershey's, but it's a lot slower than we have now. It took about 10 minutes to make one design. Our candies now print in under 5 minutes, no matter what you design, so it is one of the fastest in the world. But watching people 10 minutes, it made it very clear that 10 minutes in a busy retail environment was too slow. But more than that, the biggest issue that we had was the usability. So what I created was a tablet application that kind of led the consumer to believe they were designing on the spot, and then it would send me an email of what they had designed, and then I would have to spot code it while they were waiting. And that took, like 5-10, depending on the complexity, 5-10 minutes. And I went back to the lab after the beta test finished, and the biggest thing that we had to sit down and make work was developing a plug-and-play design software application that allows a 3-year-old kid, an 85-year-old man to design something that is then perfectly sliced, and a perfectly sliced G-code is created automatically and sent to the printer, and it prints out perfectly every time in under 5 minutes. And that's the reason we went through that process. Then we launched the actual printer that we have now, and I'm going to show you some videos of that in a second. at the ISM, which is the world's largest conference for confectionery, food, sweet, snacks, food. And we won the Product Innovation of the Year. And that's kind of like the Oscars for candy. And so it was a massive, massive good day for us. Katjes had never won it before, so together we were both very proud. And then we actually launched our first printers into the market just a year ago this month in April of 2016. So let's see if I can get this video to play. It's always fun when you have videos, you never know. This is the beta store in Berlin. This is the very beginning.
People are able to increasingly create products that are customized specifically for them, any occasion or any mood that they might have.
See, that's my fake app that they thought they were using, yeah?
That, along the lines with the fact that all products from the Magic Candy Factory are vegan, dairy-free, gluten-free, and all natural, means that everyone from all walks of life can enjoy the experience we have here.
Okay. It goes on to show you a little bit more, but it's not that important. So yeah, you will have seen in that video, the machine was huge. Did you see it? The thing covered in wood? We coated our printer in wood to make it seem more natural as opposed to being like food made in a lab. And that actually has been really well received by the customer. So our printers still are focused around the idea of natural magic as opposed to high-level science. And you will have also seen me like this next to the computer. That was me doing the spot coding for the designs that people made on the fake app. So what is our principle around the Magic Candy Factory? Three things really. It's an FDM printer in general, which has been adapted and specially created in order to align with the regulations for FSA, FDA, etc. for food preparation and live food preparation on site in commercial and public avenues. And this is not super easy to do, and this is one of the big problems with food printing. People who are using 3D food printers in a lab or at expos don't have to abide by any of those rules, so they can create really cool looking stuff, but whether they'd be able to actually sell it to someone in an actual retail environment is a different story altogether. Laser bed printing has a lot of problems with chemical transference, etc., which make it very difficult to pass. So that's the first step. The second step is our custom plug-and-play design software, which takes any design that the customer wants, and I'm going to show you lots of examples in a minute. But you can draw something, you can upload photographs, you can write words, you can type in things, you can choose from bunches of 3D shapes, and then you combine them all on an A5 sheet card. And this system uses a triple parametric algorithm in order to make your design as big as possible without ever going over 5 minutes print time, and it slices it perfectly and prints out perfectly every time. And that's a game changer in my opinion. And then lastly is the ingredients. And you guys, I brought samples. There's about 100, so after we finish, grab one as fast as you can, maybe share if you can. I could only fit so many in my suitcase. But they're basically made from a very special blend of ingredients, and the reason for this is, you talked a little bit, Christopher talked about materials. Not all material will print very well, and regular gummy candy recipes, majoritively are based in gelatin, which is coming from animal bones. It's taking 3 to 5 days to dry. So can you imagine what would happen if we put that in a 3D printer? It would make a puddle of nothing, and so it wouldn't create a very meaningful design. It certainly wouldn't create a positive experience for the consumer. So we've developed a special recipe, has 3 patents, both our cartridge delivery system and the ingredient base itself. And this is based in apple pectin, and this dries in 3 to 5 seconds, allowing us to build layers, create things like the Eiffel Tower, etc. And we can actually build things up into, anywhere between, well, we use 1.2 mm diameter nozzle on the system. That's the way that the slicing stays perfect every time. But we have built things all the way up to about 15 centimeters. So yeah, it's really, really cool. So those are the 3 things that make it special. this is what the printer looks like. And then we did this on purpose. We could have made it white, like a lab. We could have made it like metal, like science-y. But we actually focus on the idea, I think it's Clarke's third law, that any significantly developed technology is indistinguishable from magic. And we think that this is a wonderful example for the public to see. They type in their design, they draw their picture, they press a button, and like magic, the candy prints out in 5 minutes. Now, we all know there's a ton of science and technology happening in the background, but the consumer doesn't really care about that. All they care about is, this is a magical device that allows me to make something special and unique for me every time. And then these are gummy zummies, because the word cartridge is not a food word, and we do not say cartridge in food. Or syringe, that's even worse. So we have a trademark name, Gummy Zummy, and inside of these cartridges, these are pre-filled. They each have their own nozzle. They're made of totally recyclable PET plastic, and they come fully wrapped and ready to go. You place one in the machine for each individual print. You push one button, it prints it out, you take it out, you recycle it, ta-da. And that works perfectly every time. And by controlling the material, and by controlling the amount, and by controlling the heating, and the actual plastic that we use, which encourages very fast homogeneous heating, we're able to ensure that the result for the customer is perfect every time. And then we have finishing sprays. This is more retail magic than it has anything to do with 3D printing, but every candy can become fizzy strawberry, sour strawberry, or glitter strawberry, etc. And you'll see those over there when you're done. All of the products that we make are completely safe for almost anyone to eat. They're GMO free, they're vegan, they're free from gluten, dairy, soy, eggs, nuts, tree nuts, caseins, and wheat. And they're halal and kosher friendly. And that means that it's really, I believe, the future of food to be able to create things that are inclusive, not exclusive. And by traveling around the world and seeing all of the different trends in different types of food allergies, and even though maybe people are not allergic to it, it's a trend to be gluten-free, for whatever reason, it doesn't really matter. The consumer decides what we make, and now we don't actually exclude anyone from our product set, which I think is the future of food in general, or should be. So this is what the Magic Design app looks like. And it is run on Windows. Magic Candy runs on Windows. We tried to run it on Apple, it doesn't work. So everything that we do is on. No, it's really great. We actually we did this in a speech. We just won the UK Tech Startup of the Year, and I talked about this in my talk. Somebody from Microsoft saw me do it, and now hopefully we get to do a little partnership and get some new stuff. But basically, this is a tablet. It's standing next to the printer. The customer walks up. What do you want to make today? Would you like to make a custom message? Would you like to draw something? Would you like to create an edible greeting card, a custom cake topping? Would you like to make our newest thing, the sweet selfie, which is where you get your photo taken and it turns your face into candy? Then they can go through, enter in all of the things that they want. Then it creates a 3D render of their design. Then they can select from any of the 8 colors and flavors where they see the image on the app changing as they design. And then they push one button, and then they're able to make it. So here's a little video that will show you how it works, hopefully. Let's see. Can you do what I do? Sorry. Oh, maybe this is it. Yep, there we go. now, also, in addition to that, and again, this is really for retail magic, but one of the cool things about 3D printing, especially when the customer designs their own candy, is watching it come to life and that instant customization, which is hard to get across any industry. So what we've integrated now into the printers is they all have a video camera on the bottom left side, and at the end, during each individual print, it automatically collects a video and creates it into a time lapse and sends an email to the customer about 3 to 4 minutes after the candy's finished with a link to their time-lapse video, which they can then share online or share with the person that they made it for example, if it was a gift, which a lot of them are. And this is amazing. So this is an example of somebody who's making selfies, and now on a daily basis you can see thousands of people all over the world making their faces and candy, and we can't believe how much this is growing on a daily basis. And it's the shareability and the ownership of the creation process that makes the customer fall in love with it, and that empowers them and makes them want to share it. You know, when you buy something like a pack of M&Ms at the store, you're not gonna be like, look what I bought on your Facebook. But this is totally different. This is like really for them, so it's different. And here's some other examples of the possibilities. You can see we can take images off the internet and make perfect replicas of logos. We do this for the press. We've been very lucky to be covered quite a lot, but also we get orders from corporates for like 3,000 so-and-so logos, and so this is a really cool side business. Over there you can see edible gummy shot glasses. These were for a party for Comic-Con. 3D shapes galore. Little kids can write their names. I mean, really, there's almost no limit to it. But one of the interesting things that we learned in the retail environment, especially in the United States, is that if you tell people they can make anything, it's actually too much. They really can't handle it. And I think almost feel kind of embarrassed that they're not creative enough to choose something. And so what we're doing at the moment is experimenting with isolating certain parts of the concept and offering just that one part. The sweet selfie has taken over because like 70% of people were making this anyway. So we thought, okay, let's see what happens if we lead with that and then just have a little secret button, want more magic if they really want something different. And the results are huge. It's doubled the rates of sale in a lot of the retail market applications. So although we want the customer to know they can make everything, sometimes to say you can make everything is too much. So here is a little video on sweet selfies. There's no music with this one, sorry. I'll sing to you. Harry Potter, everyone recognize him? This is another actor. Quiz at the end. And this is really fun. So in the stores, we have like a little section where people can come, they get their picture taken live. So it's kind of like an edible candy photo booth. And then it's printed out, and then they take it away. And mostly, I think they don't eat it except for little kids who definitely do eat them immediately. Okay, and I'm just gonna, this is some examples of celebrities that we got to make their faces when we were backstage at Comic-Con and the Grammys. And what we did was we did these selfies of the celebs. We had them autograph one of the versions, and then we auctioned them off and raised, thousands of dollars for different charities at each of the events, which was super cool. It was really great. And then this is press stuff, but I'm just going to stop that because I'm going to talk about it in a minute. Here's an example of a retail location who's doing what we call the Famous Faces wall. You make loads of celebrity faces and it creates this amazing engagement, almost like a museum installation where you can go up and go, ooh, who's that? And you can hopefully recognize some of those people. I understand there is glare, but Beyonce, David Beckham, David Bowie, Elvis, Marilyn Monroe, Justin Bieber, etc. And this is a really fun thing to do for a shop window or at the opening of the store, because it actually makes the whole thing like what we call edutainment. It's entertaining and it's educational. And so since we launched, it's been very exciting. We have over 100 retail printers in the market now all over the world, 25 locations globally operating in a permanent basis, and then we have a pop-up store rolling concept in the UK, which moves about 10 locations all over for different types of events. And this year we're really excited because we're continuing to expand the retail side, but we also have a ton of very cool events, very big ones that we're working on, and really pumped for the end of the year when we launch 5 locations in an amusement park, which I'm not allowed to talk about yet, but it's going to be incredible. It's with a massive, big company, and we're really excited to see the application of the 3D printer and the candy in an amusement kind of avenue. So these are some examples of places where we are. So this is Dubai. This is Candylicious in the Dubai Mall, which is I think they argue about it a little bit, but they say that they're the biggest, busiest mall in the world. There's some examples of when we did that launch. It was great. That was our first ever launch. That was the store that launched in April of 2016. This is Dublin, Candylicious and Duty Free. So this is a duty free application where people make candy for gifts to bring home for people when they're traveling. This is HIT, which is a kind of new innovative shopping experience store in Germany, and this is the launch for them. This is Dylan's Candy Bar. We actually have printers. They have 2 to 3 printers per location, and they're 5 flagships in New York, Chicago, LA, Miami. And that's Dylan. Ralph Lauren is her dad. This is her concept to bring candy and experiential candy to the masses in the US. And then this is the UK pop-ups that we did for Christmas, and they're rolling them back out again now for the next one, which is for the spring launch. We work with Luti in France. They have, I think, 7 locations now, and they call it the Lab Creatif, but it's our printer. And then this is just some of the examples of the media impressions that we've got. So I think 3D printing obviously always gets press, but there's different levels of press. And I think one of the hardest things to do as a small business is to get press, consumer-facing press. Trade press, it's great, we all like it, but to get consumer-facing press, it's not as easy. And I think the concept that we've developed here, the way it combines something which everyone knows is important, it's a trending topic, 3D printing, but with the fun and colorful medium of candy, and with the usability factor, it's had a huge response, and we really have earned a ton of press for it, and without this, we would never ever have grown to the size that we have in such a short period of time. We are featured in the Daily Mail. The Daily Mail reporter actually flew to New York and did a 2-page spread on us when we launched in the New York store. It had 43 million impressions. It's that's really helped us a lot. And then these are just some of the TV programs that have featured us. And in the year since we've been in market, we've had 3 billion impressions on our brand, coverage in over 30 countries, over 700 print and online features, and 65 television spots and counting. And our media monitoring agency tells us that this is worth over 100 million euros if we had paid for this as advertising space. So this is a huge leveler for SMEs that are developing cool concepts for 3D printing, for food, for anything really, but this is my experience myself. Without this, there's absolutely no way that the number of people that have engaged with our concept would have. And without developing a really cool and unique concept, you can't get this kind of coverage. So we're extremely grateful. This is some examples of events that we've done. The events industry is something that I didn't really think about in the very beginning when developing the concept, but it is taken off in a huge way. People want something fun and engaging at their events, and Magic Candy offers that for all different kinds of parties. Little kids' birthday parties, weddings, backstage at the Grammys, etc. So it's been amazing. This is Nerd HQ. This is Comic-Con, where we were in the green room. This is Heidi Klum's Halloween party. Sadly, we're not allowed to show you a lot of the pictures from that party, but we were there and we made selfies for lots of people. We just did the opening of the combined Nickelodeon animation studios in Burbank, California, which was an event for 3,000 people to basically build their biggest joint offices, and we made over 1,000 gummy selfies through the event for all of the people that are on their creative teams. That was an awesome event. I really enjoyed that. And these are some of the examples of events that we've, different ways that we can do it. For Nickelodeon, we've done some things which we're working on with them where we can actually put an applique on the front of the printer to be focused on their type of event. And we just tried this for the first time the other day, and I was like, it'll never work. You can stack the printers, at least one on top of another, and we had all 8 of them going at once in the office. It looks amazing and creates an incredible feature for any type of an event. We can also customize our tablet software, the emails we send out, so that our customers, no matter who they are, can have a custom solution, not just for the end product, but for the entire engagement of the brand experience. And before closing, these are just some of the awards that we've won. I need to update this slide actually, but it's really great because what people are reacting to is, I think, like I said, it's 3D printing, but it's in such a fun and exciting way that it's easier for people to pick it up, walk with it, talk with it, understand it, and use it. And I won't talk about that. Future Magic. So basically, there's some exciting things happening in Magic. In the very beginning, when I started the concept, I didn't even know, first of all, whether I would be able to get it to work, and then second of all, whether the customer would even want it. Now, after a year in the market, we have a lot more confidence that the customer does want it. So we're actually developing 3 new technologies for our next level of printer. And we're also bringing all of our manufacturing back into the UK. We've worked with lots of amazing partners all over the world in order to bring the concept to market. But in a perfect world, we want to control all of that by ourselves in the UK. And then finding collaboration partners. We're already collaborating with quite a few companies, but we're working on some really neat kinds of link-ups, hopefully, for the near future. And then the amusement parks thing. I mean, really, when I started developing the concept, I had a dream that it would one day end up in, why not have magic candy in the Magic Kingdom? Doesn't it make sense? I feel like it does. But so I believe that this is a huge application for the concept, and I think that there's a lot of expanding opportunities for that. But yeah, and that's it. This is me and my team, my small team. We're 7 people in the UK who do all of this wonderful stuff. And if you want to take a picture, you can contact us anytime. And of course, this presentation will be available for all of you after the talk. If you want it, I will make sure that Christy has it and you guys can share it. So do you want to wait to do questions after, or do you want to do it now?
No.
Now, okay, any questions?
Anyone have a question?
Hello, Melissa. What's the business model now? You have the licensing, or you provide a turnkey solution to your clients?
For the retailer, you mean, or for our customer?
Any kind of collaboration.
Yeah, so basically we customize that too, but in general, the majority of our accounts lease the printer from us, and then they buy the ingredients from us on a continual replenishment basis, and we provide things like the software license, and depending upon the size of the customer, we agree to a promotion and marketing campaign structure that's together as a team, and sometimes even exclusivity for certain parts of the market in order to ensure that we are really partners, I think, is most importantly.
Okay, so I need your card.
You need my card? Absolutely. Afterwards, I will be here in the break and you can grab one.
Okay.
Thank you.
Hi, Melissa.
Hi.
I just have a question about funding. Is it all funded by yourselves, or how does the funding process take place?
So far, the funding has all been provided by myself and Katjes, so we're both shareholders. We've issued, injection funding and shareholder loans. For our next growth cycle, we will look at other things because it's quite a big jump. But it's really exciting to see that in less than 1 year in the market, we are almost at a position to be self-funding for the current ops. It's only the growth that we're going to experience that we need to look at some additional opportunities for assistance with that. So yeah. If you're interested, I can give you a card afterwards for sure. Yeah.
How many cards you have today?
I hope I have enough.
So any question? So, okay.
What's the availability now in China? Like if this machine can be actually go back to China and the food licensings and all this?
We have a partner in China. He's sitting over there. And we're working with them on the events industry mostly, but there's lots of opportunities for other things too. We do not have printers in Hong Kong at the moment, so yeah.
And another question is, once you take those photos, are those photos need to be processed by your headquarters and then in order for the customer to print it right away, or?
No, the software actually, originally we did it completely in the cloud. But what we realized is that's quite a risky strategy in a retail environment when Wi-Fi can be changeable dependent upon usage. So we actually have on our tablets deployed remotely every single night. The tablet hooks to the internet and downloads any any new things that we've created, any new technology, any new shapes or whatever. But when the system is running during the day, it's running on a remote server download, so you do not need the internet. The process of the conversion of photos happens automatically. When I say automatically, it takes 15 seconds, 15 to 20. And then you'll see the 3D render pop up, so you don't need, our HQ does not need to be involved at all. It all happens remotely with your software license.
So for example, like if I have this in a cafe, then the waiter or the guy that operating it, does he need any technical skills to sort of like operating these kind of process?
No, absolutely not. We developed the concept so both the consumer and the retail associate need not know anything about 3D printing. I would say the training process takes 3 hours maximum for a large group, and it's easier to use than your espresso machine.
Any more questions? I think everyone is expecting the candy slice there. Before we finish this section, I have some suggestions. Since I think we have over-recruited some persons here, I don't think everyone can get one pieces of this. And I believe maybe the VIPs and the officiating guests can have it later. I make an arrangement with Melissa later, see how we can ship some more to your guys. And for the rest of audience, if you are coming from one company, I suggest you take one for your company. So we behave and and take this. And after this, I walk away and I'm not going to see anything else. Okay. So let's have a break. When we all come back in 11:30. I believe we will have some coffee and tea coming soon because our break is released earlier. Okay, thank you very much. Thank you, Melissa. Also the CEO of Emerging Object, which specializes in innovations in 3D printing architecture and building components. He will share how 3D printing could be applied in building and construction industry successfully. Ronald, please.
Thank you very much. I'm looking forward to sharing with you many of our innovations, and they may span the food industry and the construction industry in interesting ways. I'll get to that in a moment. For the most part, our company explores the way 3D printing can enter into the architecture and construction industries. And we find that salient because you see this graph here demonstrates the innovations in construction since 1996 to the present. And it's coded by location and also material. And you can see that not a whole lot has happened since 1996. This is Barak Koshnevis at the University of Southern California, who developed contour crafting. And much later, it's only recently that we see an exponential curve, which means that architects and builders will be specifying materials and components that are additively manufactured in the future. I'm going to share with you several of those innovations that Emerging Objects has produced in our R&D lab. And I'm also going to talk to you about our ethos and our building assemblies. Now, architects normally use 3D printers in this way. They use them to evaluate models, to print out small models and look at them. And if you have been following the architecture and construction industry relative to 3D printing, you see things that look like this. Very crude prints made out of extruded concrete, and often the machine is larger than the object itself, which poses many limitations in terms of craft and in terms of speed and precision. I'm going to talk about our innovations which consider 3D printing architecture for the 21st century. We have several ethos, one being that we often look at traditional construction practices as the way to move forward, particularly looking at smaller building components. So rather than thinking of one large machine that prints one material as a solution for architecture, we believe that architecture is comprised of many different kinds of materials: hard materials, soft materials, woods, cements. We also believe that building materials should come from sustainable and renewable resources, or should use building materials in sustainable ways. So I'm going to talk to you about some of those as well. As I mentioned, we began with the kind of most common building element, the brick. And we've explored the way that very accessible technologies can allow for scaling up in terms of architecture. And we've begun to explore several experiments that look at ways that additive manufacturing can enter the building industry. So we begin with a single brick. How can we introduce complexity and craft into a system to create 3D printed walls, for example? Walls that use one single brick that can be rotated randomly and be assembled very simply, entirely with 3D printable components, and create a complexity that uses the material, the materialities, translucency, various colors to produce customizable architecture. If we take this to another extreme, how can then we begin to test the same kinds of small 3D printers that you might find on your desktop to produce larger scale? And in this case, we explored the way a farm of 100 3D printers could produce a very small structure in just a couple of weeks. This particular structure has over 3,000 parts. And if we take into account the idea that additive manufacturing can produce difference for free, what we don't often take into account is that managing difference costs money in architecture. It requires someone to file, manage, and to sort through potentially 3,000 different parts. So in this case, we were looking at ways that we can create a doubly complex surface with the minimum number of parts. And in this case, we have about 54 different parts, and they happen to be, in this case, encoded by color. And therefore, the building instructions are encoded into the architecture itself. So purple goes in one place, white goes in another place, translucent in another. So you know exactly where the components go, which makes building a complex structure very easy and very fast. And this project we call the Star Lounge. And if we make smaller components, the idea is that we could assemble those smaller components into larger components so that we could prefabricate components of architecture and ship them to the site so they can be assembled later. And here's a video that demonstrates the assembly of the Star Lounge. You can see the structure is broken down into the larger star and hexagonal components, and then they're simply assembled quite quickly. Nobody believed it would work, but the board was a part of the design. But for us, plastic wasn't a material that we found very interesting. These are all made out of bioplastic made out of corn. But we wanted to explore other materials. And because this is a conference that begins in architecture and food, I'm going to tell this story from the perspective of the kitchen table and the materials we invented beginning on the kitchen table, specifically coffee and the coffee grounds that one throws away, and the materials we developed using coffee grounds for additive manufacturing. So we took the coffee grounds that one disposes every day and we converted into a 3D printable material. And what did we print out of that? We printed a series of coffee cups. So these are 3D printed coffee cups made out of coffee. And of course, if you have coffee cups, then you need something to stir the coffee with. And so we made spoons made out of 3D printed sugar. The 3D printed spoons you see are teaspoons. And so we make teaspoons out of sugar that are the volume of a teaspoon, half a teaspoon, a quarter teaspoon, a teaspoon and a half. And so these are our sugar teaspoons. But it doesn't make sense to print teaspoons out of sugar, so we printed teaspoons out of tea. These are our 3D printed teaspoons that are printed out of tea that are the volume of a teaspoon. And of course, if we have teaspoons, we also need teacups. These are our material innovations that explore tea as an additive manufacturing material to make 3D printed teacups. And if you have teaspoons and you have teacups, then of course you'll have a tea set and you need a teapot. And so we decided to 3D print a teapot as well, but what teapot did we choose? I don't know if you're familiar with this teapot, but this is called the Newell teapot. And this was the first object that ever was translated and rendered on a computer back at the University of Utah. And so the Newell teapot was taken into the computer many decades ago, and now we've brought that back into the physical world. This is the Newell teapot, 3D printed out of tea. And of course, this is what we call the Newell tea set. Looking around the table even more, we were interested in the salt as a potentially additively manufactured material. So we 3D printed some salt shakers, but that in fact wasn't very exciting or very useful. But we were much more excited about the idea that in the San Francisco Bay Area, there are several hundreds, thousands of tons of salt produced each year in these crystallization ponds, which makes salt a very available and local material, makes it very inexpensive, and only wind and sun is used to produce the salt. So if you ever fly into San Francisco, you'll see these beautiful ponds that are multicolored, often pink, and those are the crystallization ponds where they bring in water from the San Francisco Bay, and they lock it in, and they let it dry over the course of the year, and it produces about 4 inches of salt each year. So we began to explore how salt can become a material for additive manufacturing, and these are some of our experiments looking at micronized salt from that landscape as a building material that can be assembled into components. We developed a polymer that can seal the salt, making it waterproof and giving it structural qualities. So we began to aggregate salt into components to think about how we might produce larger structures made out of 3D printed salt. The company that owns the land in the San Francisco Bay has been slowly selling the land to produce housing, and they're currently planning on constructing over 40,000 houses in this landscape. So as a theoretical and conceptual exercise, we wondered, well, could salt be part of the building palette that would produce that architecture? So we took it upon ourselves to produce an experiment that explored salt as a building material. We were inspired by the Inuit igloo because the Inuit igloo uses the material from the landscape to build the architecture itself. And so we made a salt igloo because it was made out of salt and glue. And if you're a Spanish speaker, you know that E means egg. Thanks. So we began to design the salt igloo looking at the forms of the traditional salt extraction practices and also the microscopic crystallization forms of salt. And this is a single brick. So whereas the Star Lounge was an experiment in really in file management, this became an experiment not only in materiality, but how we could produce a structure very quickly. Fundamentally, a lightweight salt tent. And so we took this form and we aggregated along the surface. Here are the salt components. Each one of the 340 salt blocks are unique. And here they are assembled together to create a lightweight shell. The shell is structural, but it's also assisted by very lightweight rods held in tension. So it's really like a salt tent. And here is the salt igloo in our lab being constructed. Here's the interior of the salty glue. Okay. You can see they're held together with these lightweight rods and very small clips, so it can be rapidly deployed, so it can be assembled and disassembled very quickly. And here's another view of it. This was a prototype that was funded by a company in Beijing who wanted to create 3D printed houses north of Beijing. So we're imagining these as prototypes for architecture. We're imagining these, in this case for this house in Beijing, as ways to enclose the interior private elements of the house, bedrooms and bathrooms, for example. But because we also have been able to create these as waterproof structures, we're imagining exterior components as well being clad, so building facades, for example. And we've explored other materials in the house, particularly for the facade, that begin to take the advantages of 3D printing to define views, to allow light into spaces in particular ways, and to define privacy using a material that we've been exploring for additive manufacturing, which is sand. Sand, of course, is readily available, and it can uniquely be used as an additively manufactured material. So we developed a series of salt blocks that could be stacked and hung as a building facade. They too are waterproof and have structural qualities, and this is what we call the Pico Rocco block. It'll also be used for sound attenuation, and because it's quite dense and quite massive, it's very much like stone. And so in another project, we began to explore how this material could potentially be used as a structural material. And being inspired by ink and ashlar masonry, how could we create a series of interlocking blocks that worked to resist seismic forces? And this is a project that we call the quake column. So you may be familiar with ink and ashlar masonry, which is very complexly cut to interlock together, and where there's an earthquake, it has the ability to disperse the seismic waves. And so we decided to take that into consideration to make a 3D printed block that could interlock very tightly with its neighbors, and that could be assembled very easily because instructions could be encoded in each block. And also it was very manageable because although each of these blocks are quite heavy, they had a handle 3D printed into the block itself, making them easy to carry. So here you see the precision of each block as it's interlocked with their neighbor. Here's the assembly, you see the instructions, so a workman knows exactly where they go in space. And this is the 3D printed quake column. Other materials that we've explored and developed for 3D printing are clay. And how could we take humankind's oldest additive manufacturing technology and apply it to the 21st century? So we began to develop clay as a 3D printable material and to begin to think of applications for this material. Some of our early explorations simply explored precision and accuracy and how we can make very thin structures. We didn't know what exactly we were going to make, but we also began to fire them as ceramics and test them with glazes so we could see what the limitations of this material are. And we also began to imagine how we could introduce this into standardized building components and systems. For example, taking the simple module of a brick, and could we have 3D printed bricks that could plug into existing brick structural networks, maybe bricks that could hold plants or water or vegetation? Could we make a 3D printed brick that was full of air pockets, and maybe that held a thermal barrier between the exterior and the interior? And in this case, looking back at traditional architecture, we're exploring this technology that uses a very porous clay pot that holds water and is suspended in front of a window. This is a technology that's used in Africa and the Middle East and in the arid regions of the Mediterranean. And what happens is, when breezes pass by that pot, it causes the water to evaporate. And in an arid climate, when the humidity increases within a space, the temperature drops, and therefore this is a passive cooling system. So we developed a 3D printed brick that could take advantage of what 3D printing can do, which was to create two levels of porosity In this case, a microporosity that through capillary action absorbed water like a sponge and held the water within the brick itself. And another level of porosity that allowed breezes to pass through it and guided warm, dry air through the brick and brought cool, moist air into the building. And so we call this brick the cool brick. The cool brick also has the advantage of being able to be attached with mortar quite simply because of the mesh of the geometry allows it to be held together very simply. And this relief that you see, that allows the surface of the brick to be in shade most of the day, so you don't have evaporation due to the sun. Other materials that we've explored are paper. We've been able to take recycled newsprint and turn it into a powder and create a 3D printable material from that. But more exciting to us is to take the over 7 million tons of wood that are wasted each year in the United States and turn that into a 3D printable material, essentially taking what has been a subtractive industry, beginning with a tree, chopping the tree down, chopping it into smaller pieces with an enormous amount of waste, and converting that into a productive and additive material strategy for useful building components. And so these are experiments in 3D printed wood with the material we developed. 3D printed wood has interesting characteristics. It is waterproof and it has structural capacity that is stronger than wood itself, both in compression, and we've introduced a fiber reinforcement system that makes it very strong in tension as well. And what's interesting is that the wood begins to look like wood. The additive manufacturing layers create a kind of artificial grain that would be found in old growth woods. These are not growth rings, these are in fact the layers of additive manufacturing, layer by layer of the wood itself. Some people say that it also looks like rusted corrugated metal or Corten metal. It can have translucent properties, and we've tested various kinds of woods, softwoods, hardwoods, and we're always thinking about how the components can be aggregated, that we're making building blocks to create larger structures. So we begin with the tile, we think about some level of aggregation, and we begin to envision wood structures that can be used for interior partitions, walls, or exterior facades that have a high degree of detail and a high degree of craft and beauty. Taking into account our knowledge with paper and wood, we begin to explore other waste materials that are found locally in California. There's an enormous wine industry in Northern California, and much of the waste that's produced in the wine industry is grape skins and grape seeds. And they've attempted to do many things with these materials, feed them to animals and use them as fertilizer, and even feed them to people. And so they packaged them very nicely in little bags and tried to sell them with little recipes of how to cook cookies with them and things like that, but nobody was buying them. So we began to explore how we can take this grape pumice and turn it into a 3D printable material. So these are 3D printed wine goblets made out of Chardonnay skins, a waste product of the wine country in California. And for Design Miami, we also produced this wine bucket made out of the Chardonnay skin, so that's a 3D printed wine bucket. Another material that we've been exploring recently is rubber. And the rubber we use is made from waste car tires. And in the United States, there's about 300 million car tires that are thrown away each year. It occurs to me that 80% of those tires are in fact recycled in the United States. But that's not the case everywhere. And in fact, in Kuwait, 0% of tires are recycled each year. And this is the largest tire landfill in the world, found in Kuwait, and it can be seen from space. So can we take waste tires and convert it into a useful material through 3D printing? So we began to explore that, partnering with a company that can micronize the rubber by freezing it with liquid nitrogen and breaking it into a powder. The material then comes into our labs, and we introduce our knowledge base to make it into a 3D printable material. And so these are some of our experiments converting tires into objects that have a degree of complexity and potentially usefulness. More recently, we begin to return to clay as a building material. And we like clay for a number of reasons. We like it because it's very natural and earth-friendly. It's non-toxic. It lasts for 30,000 years as long as we know. And how could we use this in different ways? The material that we developed before was a powder-based clay, and we could produce very complex objects. But what we've been doing more recently is not thinking about the material or the object, but we begin to explore the way that the machine actually works. And let's see if I have a video here. I don't know why it's playing. Suddenly my computer froze. Let's see what happens. There we go. So again, much of our work has been in the realm of material design and also object design. And so in this case, we're no longer thinking about the design of the objects, but the function of the machine and how the machine contributes to the making of the object. So we're making strange objects, and we don't know what this is going to, or where this is going to go, but we're making objects that look like this, hairy objects. We're making objects that look like this, kind of curly objects. But to us, this is exciting because it opens up new possibilities for the making of ceramic objects that we may find have unique aesthetic qualities, functional qualities, structural qualities. I mean, in some ways, this is art, but in other ways, this is science. This is interesting to us, and we want to see where this research takes us. So these are objects made out of ceramic that then we can fire and glaze. They become waterproof and porous. And so this is a body of research that we created that's called G-Code Clay. And G-Code Clay explores the machine behavior, creating a series of ceramic objects that sort of defy what we think ceramic can do, but also some of the fundamental preconceptions of what 3D printing ceramic objects can do. Mostly we're struck with the kind of layering of 3D printed objects through extruded clay, but in this case, we can make clay that looks much more like textiles and woven. And you see in the background, we're also exploring the way that these can translate and scale up. And we're pushing these to particular limits, thinking about texture and surface and pattern that, again, may have unique structural qualities, may have performative qualities, but also aesthetic qualities. These are some of our experiments in thinking about how these can be used as a wall cladding systems, for example. This could be used on the interior or the exterior. In some cases, the entire structural system and hanging system is 3D printed and customizable. And you can see the unique textures that these produce. These are textures that would be impossible to be made any other way. And so more recently, we're beginning to 3D print a micro house. And this will be finished in just a couple of months. But the exterior of this micro house looks like this. It's entirely made out of these 3D printed ceramic rain screen hung on a 3D printed surface that's translucent. The interior of the house is the 3D printed bioplastics and corn. And even the furniture inside is 3D printed as well. And this is an example of another wall that exists within that micro house that's 3D printed out of the waste that we produce in our own lab. And so we see some Chardonnay grape skin material, some of our iron oxide free cement, some of our Portland cement material, some of our wood material. And so this is interesting to us because in some cases, some of the materials begin to cross-pollinate, and we see that there's hybridized materials being created just accidentally because these are waste materials. And so we're often asked, do you print multi-materials? And so we began to explore that as well. This material sample right here is grape skin at the top and 100% Portland cement at the bottom with a gradient in between. And so these are some recent experiments with complex forms that are just exploring these material qualities. We don't know what it means necessarily to have a geological material at the bottom and a biological material at the top, but it opens up some interesting possibilities for architecture and beyond. And we began to push this even further. So don't ask me why we did this, but this is curry at the top and Portland cement at the bottom. And you can see really how beautiful that is. Other materials we began to explore in the same way through gradients are ceramics as well. And so at the top is a porcelain, and at the bottom is a high fire clay. The top is translucent, the bottom is opaque, and these are a series of objects that we call bad hombres. And these bad hombres mix materials in different ways through these gradients. And these are high fire, non-porous ceramic objects. And so you can see, even though these are vessels, we're imagining these for architecture, and we're imagining the potential of creating unique building components in these very same ways. You can see it's not only at the larger scale, but it's localized in each extrusion that you find some of these gradients occurring. And we're pushing these to the limits of what the material can do, really allowing them to pull out of the object itself. And again, we're always imagining these as an endeavor towards architecture. And we're always looking back at traditions as well. So we're wondering how we might scale this up in other ways rather than components. And so more recently, we began to endeavor into hardware itself. But the lessons that we've learned of attempting to make a machine larger than the object itself, we want to avoid. And so this is a 3D printer that we're developing that is a polar 3D printer that can print an entire room, and then the printer can be pulled out of the room to print another room. So this is under development now, but also we're beginning to explore how we can extrude clay to produce ceramic rooms in very traditional ways. But right now this is a manual 3D printer. But we're imagining how we can produce much larger objects, much larger components made out of fired ceramic, potentially producing entire spaces or forms. So whereas we're looking back, we're also looking forward. And in this case, we see this house in Cameroon where the surface looks very decorative and ornamental, but in fact, each of those surfaces, let me go back a second. Each of those surfaces is actually a scaffolding built into the surface so that people can re-plaster the building every few years with mud. So we're wondering if this technology has the capability to impart beauty and form and structure into the 3D printing of architecture. So I mentioned that some of those material studies were gradients between grape skin and cement. So the last material I want to talk about is cement. And I mentioned up front that many of the experiments in 3D printing and architecture have to do with creating concrete and extruding wet material, which we find to be very problematic. But again, we're looking not at structure, we're looking at all the other surfaces of architecture, the interiors, the facades, ceilings, and walls. And so we've developed a material made out of Portland cement that can create very complex and refined structures without the use of any formwork. In the US, formwork costs 60% the cost of construction. So basically you build a wooden structure, fill it with concrete, and take the wooden formwork away, and sometimes that goes into landfill. Of course, we can grind it up and turn it into 3D printed wood. But our 3D printed cement is very precise, it has translucent qualities, and it looks like concrete. But the difference is, it's also extremely lightweight. So this object, which is about 5 feet across, is a prototype that can be held together with paper clips. So you can imagine how that can be used in wall construction as a surfacing. So we can make very complex components, and we can deploy those complex components to create complex objects quite quickly. As in the case of a bench we designed, a seating area we designed at the edge of the pier in San Francisco, that was inspired by the sea slug, which was discovered off the coast of California. So we called ours the sea slug. Again, we always look back at traditional ways of making. This is called a karakutsa tile, which again can be randomly rotated. So we're really only designing one tile, and we're allowing the computer to randomly rotate it so we can create very complex patterning that never repeats itself. So a way to think about design that doesn't bog down the production. And that's extremely important in 3D printing, because what we've discovered that when we have a farm of 100 printers, we don't want those printers not printing. We want them printing all the time, and design can actually be a bottleneck. If we have to sit and design every unique object that we're going to take to the printer, that will take forever. So we have to increase our design speeds as well. And so this is a process where we can create the design of a bench. We can tell the computer, these are the limitations of the size of the machine, and this is the thickness we need for the structure. And we can deploy that block on this surface, and we can 3D print all those blocks quite quickly. And here they are, cured, being assembled. And this is the final bench that we call the seat slug. And what's exciting to us about this process is that in architecture, architects create drawings. The drawings often go to craftsmen who create shop drawings. Those might go to engineers who create engineering drawings. Those come for verification back to the architecture. This skips many steps because we can also do structure analysis in the computer. And so we go directly from the rendering to the 3D printing of the structure. So as I mentioned up front, architects use 3D printers in this way right now, which is to 3D print objects and models to evaluate the form and the space and to make decisions about how they might scale up at one-to-one. But what we're doing now with these material advancements is we're able to very quickly move from using the technology to evaluate and use that same exact file to make the actual structure. This project we call Bloom. It's made out of 3D printed iron oxide free cement. It's comprised of 840 unique parts that are assembled individually into 16 larger building components. And again, we're looking at ways that we can increase our productivity in design. So we developed a strategy where we can design using images, and the black and white of the image would tell the surface whether to open or close. So we can create figural patterns like this that have really beautiful effects. You can see the blocks 3D printed in the assembly of the structure in our lab. And the structure is quite simple. It's a rotated plus sign, and that curvature gives it rigidity. So the plan is this way, and the top is this way. The bottom is about 6 inches thick, and the top is about 1.5 inches. We did the structural analysis in the computer, and it was assembled quite rapidly. We see the structural ribs inside, and we see the old brutalist concrete building, the new 3D printed concrete below. These are the 16 panels that it was broken down into, because after we constructed it, it had to be shipped to the company who sponsored it in Thailand quite quickly. And so here it is in our lab, then dismantled and reconstructed. I'll show you a video of this being assembled. So you can see each of these 16 panels is quite easy to transport and carry. And so just a couple of people can actually hold one of those panels and put it in place. The material itself has a compressive strength of 4,700 psi, which is actually stronger than typical concrete. I'll let the video run so you can see not only the party, but you can see its dismantling. So again, we're often looking back at tradition, and someone mentioned to me that this looks very much like these traditional houses in Ghana. And what I think is exciting about moving forward in 3D printing and architecture is that if we think about the past and we think about the future, rather than seeing that as a spectrum of technology and the past and tradition being at one end and 3D printing being at another, what we're trying to do is connect those two ways in really elegant and beautiful ways. So thank you very much. You can find more information about us at emergingobjects.com. Thank you.
Thank you, Ronald. Anyone have questions to Ronald? 大家都可以中文發問嘅，如果有需要，我哋盡量翻譯啊。我哋有建築業嘅朋友喺度。
Hello, Ronald. I would like to raise a question in developing of the complicated shape of your artistical building fabrics. Is it just purely come from the computer to develop the shape of the building?
These shapes, these forms, are all designed by myself and my partner. So these are also our designs. So our company is comprised of myself and a partner and a couple of employees who man the 3D printers because there is an amount of labor involved. But we do all the material development and all the design of these structures.
Yes, that was so impressive. I love it. Can you buy a Star Lounge? I want one.
Can you buy a Star Lounge?
Yeah, I want one. I think it would be awesome to have one in our office, but also for events and things. I think it's amazing. Is it possible?
Yes, I mean that's the idea. I mean our business model is, and we're sort of in the very ground level startup phase, but we can imagine scenarios where we have, and maybe very much like your business in ways, that we have a standard set of designs, blocks, let's say, or tiles, and maybe a set of possibilities, like we have to clad this back wall, it should be very special. Mm-hmm. We can have those dimensions. Someone can go in the online interface and say, all right, these are dimensions, this is the block I want. Maybe allow them to do a couple customizable things to that wall, give it some dimension, pull it out, and then all those blocks would be delivered to the site and they could be assembled very easily. More complex shapes could be enclosures for events or for rooms in larger buildings. But yeah, that's sort of the model.
I think it's perfect. The way that you can take it up and back down again really quickly makes it really, I think it makes it very attractive. And even like for someone like us, we have tons of 3D printers. So you could even give us the license to the codes and we could print them ourselves in a perfect world. Yep. You know, like it's interesting. So anyway, yeah, we talk about it later, but I definitely want a Star Lounge.
Trade him back for candies.
Yeah.
Yeah, candies for Star Lounge.
Someone's there?
Hello, Ronald. I just wonder, have you guys followed using recycled plastic as a material, like recycled bottles? Can you make them a powder form and print it?
Yeah, I think the way to go with recycled plastic is an extrusion process, and most of what we've done is the ink jetting or binder jetting technology, and so moving into powder. But we are now working with some partners at the University of California where I work, because we are becoming a zero waste campus by 2020, which means all waste, because we'll produce no waste and we'll recycle everything in-house. So one of the things that we're doing is we're going to start sorting all of the various kinds of plastics and doing various things with them, and one of those things is converting into a 3D printable material. That's not going to be a very big part of this recycling endeavor, but it's going to be one of the things that we're working on.
Okay. And I saw many students in your PowerPoint. So, yes. So did they contribute in the design, or they just cheap labor? Did you
Yeah, cheap labor. They're actually not that cheap.
They have to pay a lot of money. School fees, yeah.
No, in fact, these are all research assistants that work in our lab, and we pay them quite well.
Can I just fly over to your university and be part of your team for free of charge for 3 months?
You have to apply to the master's program at the university.
How much?
I think tuition for out-of-state international is $40,000 a year at the University of California. It's quite reasonable.
US dollar.
We pay you to work
US dollar. Okay. And anyone else? Questions?
I don't have any question, but I just want to make a very good compliment on your project, because I've seen a lot of 3D printing architecture. I'm an architect anyway, so I've seen a lot of architecture applications in terms of 3D printing, but you have the most variety of portfolio using different kind of materials, and it's very, very meaningful. And I've been taught I taught in AA, in Ballot, in different universities, and most of them are using like very industrial printing technique or robotics to create architecture pieces or installation without any sort of content. They're just like sculpture pieces or furniture that using high tech of technology for printing, but you are actually using like recycling materials, trying to solve some problems in terms of architecture tessellations using low tech printing machines to develop these large scale architecture pieces, which is, I think, is very amazing. And I think that I would like to collect this in Shanghai Museum, like for my architecture. I mean, I have a 3D print museum in Shanghai, which we can also do a lot of these things, and I would like to invite you to come to give a lot of presentation to the Chinese audience in Asia. And thank you for your presentation.
Thank you. Appreciate that. And I'll just make a comment that I think is important, that many of the advancements in 3D printing and architecture are done by mechanical engineers. And so, no offense to any mechanical engineers in the audience, but I think that part of the dilemma is that mechanical engineers are very good at making machines, but not very good at making architecture. And so, whereas machines are very complex in terms of their componentry and assembly for working, buildings are not. They're not very complicated in terms of assembly, but they are culturally complex. And so that cultural complexity relies on materials and a material palette of difference, and also forms that one could respond to as a human. And so this is our perspective in developing this technology. Thanks.
So, no more questions? Okay, and then we can go for lunch, and we all come back sharply at 2 p.m. Before we go, I have to announce something important. We have, thank you, Ronald. Thank you so much. We will have 2 enhancement one-day workshop for the catering and for the building industry separately. The enhancement workshop for food industry will be on 19th of May. You already have the registration form on it, because we only have 40. We only have 40 pages for it due to the limited room for using computer. For the other enhancement workshop for the building industry, we will have it on 23rd of June. We will have another German guy from the software company called Alta talking about how to use computer simulation to optimize the building material. And thank you very much for the Hong Kong Institute of Architecture. They already granted 7 hours of CPD for that event. So if you guys want to register it, do it now. Okay, let's go for lunch and see you all in 2 p.m.